physics, if that's correct. And so we have Roger Fu from the Department of Earth and Planetary Sciences here, who's actually putting diamond to good use, aside for jewelry and getting married and other things, cutting things and other good purposes to use for it. It turns out you can actually really use the magnetic field sensitivity to image magnetic behavior in rocks, and he's going to tell us about that today. He's an original Harvard student as undergraduate, and then got his PhD down the street at MIT.
Great. Yeah, thank you very much. Thanks for inviting me to give this talk. So I'm Roger. I'm an assistant professor in Earth and Planetary Sciences here. And for the last 4 years or so, I've been working very closely with Ron Walsworth's group. We've been developing an NV diamond-based imaging device to measure rock samples. We call it the QDM, Quantum Diamond Microscope. You'll see pictures of it very soon. So I'd like to talk to you about some applications of this QDM and how we can use it to understand magnetic fields in the early solar system, both by measuring meteorites as well as Earth rocks. Okay, so I'll start with just a little timeline of the solar system. Is this a pointer? I like it. Okay. Let me just start with a timeline of the solar system. So the solar system is about 4.5 billion years old. And it turns out that the planets, as we know them today, formed over a very short percentage of that 4.5 billion years. So I'm zooming into the first 100 million years here. Year 0, I'm going to define as the time that the molecular cloud collapsed to form the protosolar disk. So we can think of year 0 as the formation time of the sun. And then the 100 million years after that saw the bulk of planet formation go to completion. Specifically, near the end of this period, we don't have a very tight constraint on exactly when, but towards the end of that 100 million years, we had the moon forming impact. This is when you had a Mars-sized body. It hit the Earth, and it created the moon. This is generally thought of as one of the last major events in planet formation in the solar system. So after this, the planets are more or less where they are today. If you go before that, during the first 10 million years or so, you had the formation of smaller bodies, so Vestas and asteroids, about 500 kilometers in size. And then Mars is a couple thousand kilometers in size. And they formed all within the first 10 million years or so. And we know that from radiometric dating of rocks from these bodies. But if we want to understand how these bodies came into being in the first place, as well as the Earth, we had to zoom a little bit back farther in time. So just into the first 5 million years here, this is when we had the formation of millimeter-sized solids in the solar system. So before you had planets, you had CAIs and chondrules. So CAIs they stand for calcium aluminum-rich inclusions. And I have a piece here that I'm going to pass around. So hopefully you guys can pass it around without too much getting up. But I'll start with here, I guess. So if you look in this rock, there's, so by the way, this is Allende, is a carbonaceous chondrite. It's a type of meteorite that comes to Earth. You can think of it as an aggregate of space dust, basically. It's little pieces of stuff like chondrules and CAIs kind of aggregated together into a rock. You can see some white irregular objects in here. Those are the CAIs. You can see some round objects that are darker in there. Those are the chondrules. So we know from radiometrically dating these inclusions in meteorites like that one that they formed within 5 million years of the sun. And these little particles, in turn, aggregated into what we call chondrite parent body. So a chondrite is a rock that contains chondrules. And these are probably asteroid size, so tens, hundreds of kilometers in size. And these things, most of them, the vast majority, we think, became planets, like the one we're standing on. But a small fraction of these chondrite parent bodies, these asteroid-sized bodies, didn't accrete into a larger planet, and they are left in the asteroid belt today, which is fortunate, right? So we can actually study them. Okay, so just to summarize, the story of planet formation in the early solar system, it goes through this hierarchical scheme. We had first millimeter-sized particles, like the one you're passing around, and then they aggregated into 100-kilometer-sized parent bodies, and those turned into planets. Yeah.
How well stuck together are if they're coming from dust or gravitational?
Yeah, initially probably very poorly. So there's a huge preservation bias, right? Because all the meteorites we see have to go through the atmosphere without breaking up. So if you actually go out into the asteroid belt, a lot of stuff is probably a lot less rock-like, more loosely consolidated. And so it turns out there's processes like shock, like impacts, and heating from radiogenic nuclides that convert these loose aggregates into more rock-like forms. But yeah, it's not clear what fraction of these bodies are actually that rock-like. Probably only a fraction. Okay, so we have this path towards planets. So how can we use magnetism to try to understand some of these processes? So I'll start with the millimeter-sized particles. So one of the most long-lived questions in planetary science has been proposed since the 1800s by Chladni, actually, the Chladni plate, Chladni. He studied these things. He wondered why there are these rock pellets that are about a millimeter in size in these meteorites. Until today, we don't have a good answer. We know that these things are little beads of melt that were flash heated. So some very energetic process heated the dust in the early solar system. They form into these little beads because of surface tension, and they cooled into little rock pellets and ended up in these meteorites. But what that very highly energetic event is, we don't know. There's some processes that have been proposed. An early one is impacts. So this is a model of an impactor slamming into a larger body. It's kind of moving down like this. You can see this model shows that you have this sort of funnel-like plume of ejecta that's heated up to about 2,000 Kelvin. So you have liquid rock kind of spilling out, and that can form chondrules. So another model that people have put out is the X-wind model. This actually came out of the Center for Astrophysics, Frank Shu's work. And this is very different from the impact model. This actually shows this is the very near part of the protoplanetary disk, very close to the sun. It's only 0.1 astronomical units. So there's this one spot here that's co-rotating with the sun. And then it's right here, the temperature is very high, so you have molten rock. The problem is you have to somehow get this molten rock into the meteorites that we're passing around, which formed much farther out in the planet-forming regions. So the way that Frank Shu and others propose to do this is this thing called the X-wind. So this point is called the X point. And you have these magnetic field lines along which charged gas from the protoplanetary disk flows out, and they actually carried little droplets of melt with it. And so you seed the rest of the disk with these X-winds blowing out little droplets of melt, and those form the chondrules. So this was proposed in the 90s and has been a popular theory since then. Okay, so the lucky thing for us is that these different chondrule formation mechanisms predict different magnetic field strengths during the time of chondrule formation. So especially the X-wind model predicts very strong fields because you're very close to the sun. You're actually feeling the dipolar field of the sun. So if we can measure the magnetic field environment in which the chondrule formed, we can try to see which of these processes are consistent with that field strength. Okay, and then a separate question that I'll talk about here. I'll skip over the asteroid phase. We'll just go straight to the planets. So did the early Earth have a magnetic dynamo? We know that the Earth has had a dynamo since a little over 3 billion years ago, but there's no data before that. We don't know that first billion year of Earth history whether the Earth had a magnetic field. To first order, one might expect the early Earth to have a magnetic field because it was hotter. So you had more heat flux to drive convection in the core. But it turns out it's not so simple because there's actually accretion scenarios depending on how the Earth was built and what happens in these giant impacts. You can actually get a compositional layering of the early core, such that you have more light elements on the outside. I'll talk about this in a little more detail in a moment. But bottom line is, it's possible that there was compositional resistance to convection in the early core. So even with that extra heat, you have a suppressed dynamo until that compositional layering becomes destroyed over time. So it's not clear at all whether the Earth had an early core dynamo. So if we can measure the magnetic field recorded by different rocks through time, we can try to back out when the magnetic field turned on Earth. Okay, so I'll talk about these two questions. First, where did chondrules form? How did they form? And whether the early Earth had a magnetic dynamo. Okay, so before going into that, let me just really quickly talk about how rocks become magnetized and how they carry information about ancient magnetic fields. So luckily for people like me who measure these things, there's a lot of ferromagnetic minerals that occur in nature. So the most famous one is magnetite, and that's an iron oxide that at the grain scale behaves like a ferromagnetic magnet. Right? That's where the word comes from. It turns out there are many other minerals that do this. So camosite is an iron-nickel alloy that you find in a lot of these meteorites, for example, and certain other combinations. Most of these minerals contain iron. And if you have enough of these ferromagnetic minerals in a rock, like this one, I'm only drawing 6 of them here, but typically in a rock you have thousands or millions of these tiny grains.
Are you talking about like physical crystal grains or magnetic domains within a single crystal?
These are physical grains, like compositionally different grains.
You can obviously have like centimeter-sized single crystals of magnetite.
You can, yeah.
But that's not what you're talking about. You're not seeing things that large.
No, none of the stuff I'll talk about in this talk uses grains that big, but in theory,
What's the typical grain size?
less than a micron, 100 nanometers, tens nanometers. So down, like small enough that most of it's in a single domain regime. Okay, so I'm drawing these in the simplest single domain kind of picture as well. So if you have this thing in a magnetic field and you heat it, that causes so that thermal energy sort of allows these grains to flip around, right? It overcomes any energy barriers to whatever direction they were in. And then the cool thing is when you cool it back down, this alignment persists because these grains are ferromagnetic. And so even if you take away that background field, as long as you don't heat the grains again or do some other energetic process to disturb the grains, this net bias in the magnetization directions will persist through even billions of years. Right? So you have this net magnetization that we try to measure in the lab. So if you run this through again with a field that's half as strong, I think you know what's going to happen. So there's less efficiency in the alignment of these ferromagnetic grains in the parallel direction.
Does it also depend on temperature? Like do you get KT encoded there as well?
Right. Yeah. So depending on the shape and the composition of the grains, there's some temperature at which KT balances out the magnetic energy.
Or this is not the Curie temperature?
It's not the Curie temperature. They refer to this as the blocking temperature. So this is when so you're still ferromagnetic, right? So Curie temperature you become paramagnetic. So this is below the Curie temperature. You're ferromagnetic both above and below this temperature, but the transition happens that KT is large enough to flip the grain magnetic orientation independent of its crystal structure. Okay, so at least for relatively weak fields, you have this very simple linear relationship. At some point, this has to saturate, right? Every single grain gets aligned. But it turns out natural magnetic fields usually aren't anywhere close to saturation. So we're in this nice linear regime where you can measure the magnetic moment and you can back out some information about the original magnetic field. Okay, that's the first and last cartoon of this talk. Yeah, no more of that. So chondrules, as I talked about a second ago, these are little pellets of rock that were heated to very high temperatures and cooled back down. So in theory, we should be able to take these chondrules, measure their magnetic moments, and figure out the magnetic field in which they formed. There's a couple complications, and probably the most problematic is that these rocks are 4.5 billion years old. They've gone through a lot of other events that potentially can perturb the magnetic remnants in these ferromagnetic domains. So possibilities include heating on the parent body. So as we talked about a little earlier, so you had radiogenic heat from these asteroids. So even small asteroids, sometimes they retain enough heat that you can unblock these magnetic grains. You unrecord the signature that the chondrules recorded when they formed. And then you also have problems with what's called aqueous alteration. So these meteorite parent bodies, they didn't just accrete with rock because there was also ices in the early solar system, water ice and others. And when these ices melted, there was actually pore fluids. There was actually a lot of water that trickled through the matrix of these meteorites. And water can react with these different magnetic phases. So the phases you see today in a laboratory are not the same phases that experienced the magnetic field when the chondrule formed. So you have a lot of potential problems. So luckily we can do some pretty simple tests to try to rule these problems out. So one is called a conglomerate test, and this is in concept very simple. You have a bunch of chondrules, so these are actual chondrules now. Actually, this is a cartoon. It's not really animated though. It's not as cool as the last one. If you had a bunch of chondrules falling together into the meteorite, they would fall at random directions, right? So these chondrules, I mean, they have magnetic phases in them, but they're not anywhere strong or like a magnet, right? So they wouldn't align to the background field. They're not magnetic enough to do that. But what they can do is tell us what the initial field was, but it's not enough to align them. So we should expect random magnetic moments in these chondrules if we measure a whole bunch of them. And the next thing, and this should be clear that if you split one chondrule in two, the two halves of it should have the same magnetic moment direction, right? Because they form in the same event, the whole chondrule, I mean. And the third point I can add that should be obvious is that we should be able to find the primary, i.e. the original ferromagnetic minerals that formed in these chondrules, right? They should be around today and haven't been replaced. So if we can check off these 3 points, then we can be relatively confident that the signature, magnetic signal in that chondrule dates from the time of its formation and not. Oh, I'm sorry. That's, yeah, I should have said that. Yeah, so this whole process of heating something up in a bias field and then cooling it back down is called a TRM. Okay, so people have tried this on meteorites before. In fact, they tried it on a meteorite that was being passed around, Allende. So Sugiura and Strangway back in 1985, they extracted a whole bunch of chondrules from another piece of that same meteorite. And they plotted the magnetic moment directions of these different chondrules on this stereonet diagram. So this is just a way to represent unit vectors. If you imagine you have unit vectors representing the magnetic moment direction of your individual chondrules, you plot their endpoints on a unit sphere, and you look down on a unit sphere from above. So these dark points are on the bottom side of the sphere. The light points are on the top side of the sphere. Right, so these are individual chondrule directions, and these authors argue that this was random. I guess it's random. It's not the most random set of directions I've ever seen, but Anyway, so that's not the point. They argued this was random, and they said that this is passing the first of these points, that you have random directions among chondrules. So a few years ago, we tried to replicate this experiment. We took another piece of Allende, dug out chondrules, measured the magnetic moment directions. So first, we did confirm this, that the magnetization directions are in fact random among the different chondrules. But we did a couple other tests. So we took it to the next step, which is we took single chondrules and divided them up. So we did it for a number of chondrules. I'm just showing 2 here. So chondrule A, we took 4 subsamples of it, and it has 4 very distinct directions. Chondrule B, same thing. You have 2 different directions. So these magnetizations in the chondrules are not uniform, which leads us to think that this magnetization, whatever it is not a thermal remnants acquired in the protosolar disk. It's something else. So what is that something else, right? We're trying to understand how you can have heterogeneous magnetization at sub-millimeter scales, which is not something you normally see on rocks from Earth, for example. So this is where we turn to the instrument that Ron and I and our groups have been building. This is, again, it's called the QDM, Quantum Diamond Microscope. And this is actually the setup that's in my lab across the street right now. I just took this photo a few days ago. So I'm going to take a little digression from the meteorites and actually just talk about this instrument and introduce you to what it does. So I'm probably on the bottom 50 percentile of like how much I know about diamond NVs in this room. You guys probably are much more familiar with the physics side of it. But anyway, so you guys probably need no introduction. So we take synthetic diamond chips. They're implanted with nitrogen vacancy pairs. The way we use it is we take a diamond. In this case, we have about 2 micron thick NV layer. And we place that right on top of a polished section of rock. And if the rock has these ferromagnetic sources in it, it generates this magnetic field that goes through the NV layer. And so if we can interrogate the NVs and figure out what the magnetic field is, we can make a map of where the fields are coming out of the sample. And from that, we can figure out which parts of the sample are magnetized or where the magnetic rings are. Okay, and the way we do this is the same way that I think several other experiments in both Ron and other groups here do it. So we have, here's just an energy diagram for NV centers. And so the ground state is split up into spin 0 and spin plus or minus 1, which is separated by microwave energy. So plus or minus 1 are degenerate when the B field is 0. But if you apply a field, they split up just a little bit by a few megahertz in most of our experiments. And the way we can read this splitting is by shining this green laser on the diamond chip. So we pump the electrons into the excited state, and when they come back down, they fluoresce. We measure that fluorescence as an image. We actually take a picture of it with a camera. And we sweep this microwave across a range of microwave frequencies. And when the microwave resonates with one of these spin plus or minus 1 states, it suppresses the fluorescence by just a fraction of a percent. And so we can measure that spectrum and then figure out what the splitting is, and then from that back out the magnetic field. So some of you are probably thinking that's a little oversimplified, and that's true. So that's the actual spectrum we see, right? So there's actually 4 sets of peaks, right? Because there's 4 different directions in the diamond lattice. And that's very good for us, actually, because we want to have the vector information of the fields in order to back out the moment direction in our sample. Okay, so we can do this, and we end up with a image of the magnetic field as a function of space on top of our sample. And just to compare the current performance of this QDM setup with other existing magnetometers. So the squid microscope, so this actually uses a standard squid, a superconducting quantum interference device. It actually mounts it in such, I'll show a picture of this later, but it mounts it as close to the sample as you can get it. And it turns out to have a spatial resolution that's limited by how close you can get. You have a cryogenic sensor, and you're measuring a room temperature sample. So you end up having effective resolution somewhere around 100 microns. And then you can get extremely high sensitivity, down to like a few tens of picoteslas, DC. And then oh yeah, and the reason I mentioned that is that there's a number of paleomagnetic laboratories that work on rocks that have a squid microscope. Only a couple. One is down at MIT, the lab where I worked as a grad student. And then another instrument that a number of geological labs use is the magneto-tunnel junction sensor. And this one has been used as a sort of complement to the squid microscope. It's much, much less sensitive, you can see, but you can get better spatial resolution. You can try to figure out where in the sample you're magnetized. Okay, so the NV covers this field. It's actually doing better than the MTJ in both resolution and sensitivity. And it's much higher resolution than a squid, as we expect. It's not as sensitive, and it'd be very hard, I think, to actually ever get to this sensitivity.
It's not
but
you can't just run it longer and get better.
I can.
It's sort of exponential, like
Yeah,
amount of time you need to get better.
Yeah, it's like root T, right? And I guess at some point you run into, power failures and stuff.
So
but
it's like a factor of 30 in sensitivity. So it's like you would have to run it 1,000 times as long.
yeah.
But if the rock has been sitting there for 4 billion years, does it really matter? Or, come back, go on vacation, come back a month later.
In theory, yeah. If we so there's a throughput issue, right? Which is I only have one of these setups now. We'll probably have two very soon. So if you want to.
But you don't need. You're not running a cryogen. I mean, the squid microscope, like you're going to run out of helium or nitrogen or something, right?
Yeah.
Because you got to keep it cold. But in yours, in principle, you could just let.
In theory.
That prevents you from letting it sit there for a long time, right?
I don't think we haven't run into anything. I'm sure if you leave it for a week, something will happen in the building, like a power surge or something. I mean, we run it for a couple of days before, and that seems to be still scale as root T like you expect it. But yeah, the bottom line is we don't have. If we had 20 of these in the same room, then I could imagine trying to do that. But I think right now, because you have to make a lot of repeated measurements. So something I didn't talk about was, so when you analyze these chondrules or any rock, you don't just measure the moment and then write it up. You do a demagnetization sequence, right? So this blocking temperature idea I was talking about, so you actually heat it progressively up. So you actually measure the same thing dozens of times at different temperature after different temperature heatings to sort of peel back the layers of magnetic history. Yeah, so, and then you need statistics, right? So you need a few dozen chondrules or whatever to do a study. Yeah, so there's not enough time to run everything that long. If I can get 20 machines though, that would be feasible. But anyway, but we're trying to push this bar down a bit. I mean, this used to be up here like a year ago, so I think we're making some progress. If anyone knows how to get a camera to just take in massive amounts of light, we have a problem with well depth right now. That's our limiting factor. Please talk to me. Yeah, we can't get a camera that has the frame rate or well depth, combination of those things fast enough we can take up all the light coming from there. Okay, cool. So going back to the meteorite, how can we use the, yeah, sorry. Yeah, so the MFM, so that you're way down here, right? Into the sort of nanometer range, I think, for spatial. Right. Yeah. So, yeah, I think there's a few problems. You want to be able to scan over a large area. So I guess in the next slide, right, this is a millimeter squared area. And the sources you can see, they're kind of separated at these kind of 100 micron scales. So I think to use MFM, you have to get, nanometer level kind of polish on that kind of area, and then go over the whole area. I don't know how much time that would take. I think it's a lot. I mean, most MFM fields I've seen are like a micron or something, right? So yeah, I think it's useful for like understanding domain structures and like one of these sources. But if you want to get a sense of the magnetic sources in this whole rock, I think this is the right spatial scale to do it. Okay. Yeah, so this is one of the chondrules in Allende, that same rock that was passed around. So you can see that with a QDM, we make a magnetic field map. You're identifying very magnetic features. So this rim, turns out this rim is packed with magnetite. That's why it's very magnetic. But most interestingly, if you look inside the chondrule, there are these hot spots that kind of form this pattern. And they correspond to these kind of darker gray regions. A little bit washed out maybe, but these regions this is optical image of the chondrule. So these regions is what's called the mesostasis. These are the parts of the meteorite, the chondrule, that reacted with water on the parent body. So if you actually take an SEM or something and look in the the mineral phases in these areas, they're actually packed with clays, which are, when you take a anhydrous volcanic rock, you react with water, you get clays. So these are actually mineral phases that post-date the formation of the parent body. So there's no way they can tell us anything about in the magnetic fields in the solar protoplanetary disk before the parent body formed. Just as a comparison, this is the map of the same field with the squid microscope down at MIT. So you can see this magnetic rim, but you're completely hopeless with resolving the interior of the chondrule. Okay, so with the QDM, we can answer the question, this third question for Allende. So there's no ferromagnetic phases in here that give you information about when the rock formed, which is unfortunate. So we turn to a different meteorite. This is called Semarkona. It's a more primitive meteorite in the sense that it accreted with less water. There's less reactions going on after the asteroid formed. And then, fortunately, we also have these chondrules. Not every chondrule is like this, but there's some of these chondrules that are called dusty olivine-bearing chondrules. So olivine is a rock-forming mineral. It's made out of magnesium, silicon, and oxygen. It's not magnetic. But in certain cases, olivine can have these impurities in it. And if you image it in TEM, and this is actually an image of this chondrule, you can see these 100 nanometer, 10 nanometer sized iron grains. So olivines with these inclusions are called dusty olivines. And these are iron grains, and of course they're ferromagnetic. So if we can establish that the signal from this chondrule, magnetic signal, is being hosted by these dusty olivines and their iron inclusions, that's a really good step forward, because we know that these iron grains formed with the olivine when the chondrule formed. Okay, so we do the same analysis. This is the same chondrule as on the last slide, but this is in transmitted light, so you're looking through the chondrule. So these black areas is where there's iron, which is opaque. So these are the dusty olivine patches. And when we superimpose the QDM map, you can see the large majority of these signals are coming out of these dusty olivine-rich regions, which is very unlike Allende, where you had mesostasis hosting most of the magnetization. So we feel pretty good about that. So ferromagnetic minerals seem to be the right ones. And then to measure the bulk magnetization of the chondrule, we use a squid microscope, because we don't need that kind of resolution, right? We're just measuring the bulk magnetization of the fields around the chondrule. We don't have to try to resolve inside of it. And a squid microscope, again, is much more sensitive in the end. So it actually uses this probe. there's a little squid circuit mounted on the tip of that, and this is mounted inside a vacuum housing with like a little window on top of it. So you can get the sensor to within about 200 microns of this sample, which is your resolution limit. Okay, so we took this chondrule, we cut out everything around it, and then that's the squid microscope map over this region. So you can see, again, it does look like this dipolar magnetic field signal is centered on top of this dusty olivine, which is nice. And we can take this map and calculate the direction and the magnitude of that dipolar source. And again, plot it into this.
So those units would be underneath the noise floor of the NV, the QDM?
Like this map last time. Oh yeah.
Single dipole, basically, it's like 100 nanotesla or something, right? So
Right.
it's below the noise floor of what you could measure with the NV center?
No, it's not any. Certainly not anymore. I don't think even back when we measured this a few years ago, we could do this with the NV. The other thing is the NV would be much closer, so you wouldn't be seeing 100 nanoteslas. You'd be seeing quite a bit more than that. Right, you're like closer to the dipole source. So yeah, the reasons for the squid, one is because this is a more trusted instrument, right? The NV was completely new when we did this.
So, but if you were going to do this today, you would just use the NV for this?
I hope so. That's the hope. Yeah, I think it's. Yeah, we didn't want to.
Rock the boat too much.
Yeah, too much in one study. That's part of it. Yeah, with NV, you can definitely detect it. It's going to be a little bit harder to do the inversion calculation, right? To go from this to a magnetization vector, you have to see the source as a dipole, or else it becomes non-unique, or less unique. So, yeah, and if you have an NV, you're really close. You see like a whole bunch of sources. It doesn't look anything like a dipole. Then you have to start thinking about how you process that. But in principle, we can do it. And we're trying to do exactly that. Okay, and then we cut two other chondrules in half and measured their magnetic moments the same way. And you can see, unlike Allende, there's actually pretty good coherence of the magnetization directions in those two other chondrules. And then we measured a whole bunch more, well, not a whole bunch, but a few more chondrules. These are very rare chondrules. This is literally all the material we can get our hands on. But you can see, even with these, it's clear that the magnetization directions are randomly oriented. So we are passing all of these criteria, we think. We have random direction among chondrules. We have uniform magnetization in the chondrules. And the magnetization seems to be hosted by the dusty olivine. Okay, so we can use the magnetization intensities to try to recover a magnetic field intensity from the early solar system. Turns out to be about 50 microteslas, a little less than twice strength of the local field here. And we can compare that to what these different models predict the magnetic field was during chondrule formation. So this is the impact model. So the impact model, according to the people who work on it, it basically shouldn't affect the background magnetic field very much in the solar protoplanetary disk. So this is basically the range of fields in the background disk that people have modeled. So it depends on where you are. It goes down as you go farther from the sun. The shock model, because you're compressing this ionized gas in a solar nebula, you're enhancing the local field intensity by a factor of about 10, they estimate. So I'm just shifting this blue band up one order of magnitude. And the X-wind model, that predicts much stronger magnetic fields because you're close enough, you're feeling the sun's dipolar field. Okay, so our data is in this green band here. So it seems like we're inconsistent with the X-wind model. I think it's almost certainly not the way that chondrules formed. Which of these other two models is more correct depends on where you think chondrules formed. And unfortunately, we don't know exactly where chondrules formed. We know where the asteroids are today. They're between 2 and 3 AUs, so in this range. So if that's where they formed, then maybe you can say you slightly favor the shock model. But then we don't really know that the asteroids formed exactly where we see them today. They might have migrated. So we can't conclude with certainty between impact and shock models. But at least we can rule out the X1 model, I think. Now we can try to do more of this kind of work and maybe answer the question a bit better. So this is a paper from just last year. And so they're looking at isotopic differences in different meteorite groups. And what they've hypothesized, and I think this is becoming more and more accepted, is that certain groups of meteorites, like these carbonaceous chondrites, we might have actually been from the outer solar system, so outside the orbit of Jupiter, whereas these other meteorites came from inside the orbit of Jupiter. So Semarkona, the one we measured, is one of these. But there are other meteorites, actually including one that we're just passing around, is a carbonaceous chondrite. It should be out here. So we actually have some of these samples. This is a CR, just a class name for a group of these meteorites. But it's a carbonaceous chondrite, so it should be coming out from much farther in the protoplanetary disk than the meteorite that we measured earlier. So we can measure the magnetic field in this. We can try to tease out whether we are perhaps, depending on what answer we get, of course, and we know that we're out here, we can maybe try to tease apart these two impact versus the shock models. Okay, so we started doing this. So this is a dusty olivine grain from one of these meteorites, GRA 95229. After a while, you remember these things, I guess. Stands for Graves Nunatak, which is a place in Antarctica where the U.S. sends people to look for meteorites, and this is where they found this guy. And this is the QDM map of it. So you can see a nice source that was sitting right on top of this dusty olivine region. We see some extraneous sources, and the nice thing with this high resolution is you can just basically block it out because you're spatially resolved. We don't have a good answer yet. We're trying to use this data, going through some of the same problems that I was talking about earlier with inverting this into a net field or net moment. But stay tuned. Okay, so yeah, so that's all I had for the first part. So this, how did chondrules form? We think is probably by either this shock model or impact-related model, or maybe something else, but probably not the X-wind. Okay, going on to the early Earth then. So how do we test whether the early Earth, the first billion years of Earth history, we had a dynamo field or not? So the best way, actually the only place we know how to do this is going to this bunch of mountains in Western Australia. This is the Jack Hills. It's an area that's geologically very interesting because they actually found single crystals of zircon, which is a mineral, that dates from as old as 4.37 billion years ago. So within 200 million years of Earth formation. And they're by quite a big margin the oldest Earth materials we know we have found so far. So we go there to gather zircons and try to use them to see if the Earth had a magnetic field. And why is this very interesting, I think? So I talked a little bit earlier about these different scenarios where you might have or not have a dynamo on the early Earth. So this is one of the scenarios where you wouldn't. You have impactors come in and make the Earth. And as impactors get bigger and bigger, the Earth gets bigger and bigger, these things slam into the Earth harder and harder. And there's a debate about how much silicates, so the stuff from the mantle, gets pulled down with an impactor when the impactor's core merges with the Earth's core. So if this happens the way that some groups think it does, you end up with a lot of light elements at the surface progressively at the surface parts of the core. So you have lower and lower density as you go out, right? Which means it's convectively stable. And you would actually suppress a dynamo until this gradient gets taken out through diffusion. So if there's no dynamo on the early Earth, then we might think this is one of the reasons why. This is maybe how the Earth accreted. Another very interesting problem about the early Earth is the idea of plate tectonics. We know that tectonics have been active on Earth for 2.7, maybe 3 billion years, but we don't know if there's tectonics or mobile plates moving around on Earth for the first 1.5 billion years. And there has been an idea that if you had a mobile lid, i.e. present day-like tectonics, you have a much thinner lithosphere at the surface, and it's much easier to get heat out of the Earth to drive a dynamo. Whereas if you have a single plate planet with no tectonics, you effectively insulate the core, and the heat doesn't come out and doesn't drive convection. So this is a model that someone made last year, and they're modeling the magnetic field strength at the surface as a function of time since the formation of the Earth, with a tectonic regime like the present day and without a tectonic regime like the present day. So we can see field or not at this age. You can maybe try to distinguish between these models. And then the last important consequence of this is that a magnetic field has been hypothesized to protect certain species in the early atmosphere from erosion from the solar wind. We think this is probably an important event, or an important reason why Mars lost most of its water content. It seemed to have had a magnetic dynamo early on, but lost it later on. So this might tell us about, knowing whether there was a dynamo on the early Earth might tell us about how much water was lost during the early Earth and how habitable the early Earth was. Okay, so the data, at least up to about 2015, looks like this. So I'm not showing any data after or within the last 3 billion years. There's more data if you go this way. But there's some studies of rocks, South Africa and in Australian rocks, that show there's a field up to about 3.5 billion years ago. And then 2015, this paper came along from the Tardino group at Rochester. They measured a whole bunch of these single zircons from the Jack Hills, that image I showed you earlier. And they found these intensities going all the way back to this one grain that's 4.2 billion years old. So they claim that the Earth had maybe a weaker dynamo than present day, but it has some sort of field. Now the problem, as you might know where this is going, so just like the meteorites, these rocks are really old, right? They're more than 4 billion years old in some cases. So they've gone through a lot of events that could have reset their magnetization. And this is just a timeline of what we think happened to the Jack Hills region through geologic time. So the zircons have some age out here, and then they were eroded into some ancient rivers and deposited into the rock they're found in today. So they're actually you're not seeing the lava where these zircons originally formed. You're actually seeing a reprocessed version of it. And then since then, there are a whole bunch of metamorphic events, so regional heating events when you have volcanoes coming up, and also fluid events when you have fluids infiltrating the rock formations and reacting with the mineral phases. So these are all potential problems. So how do we make sure that the magnetization in these zircons have not been affected? So we use the QDM, as you probably know the answer. And we measured the magnetic field in a large number of these zircons, more than 300 of them. So we just zoom in. You can see that, I don't know if you can see it, but you can see these outlines, right? So those are the zircons. And then the red and the blue are the magnetic signals. So that's where we see the magnetic signals, right at the rims of these zircons. We can zoom in on one of them. So that's the zircon. That's the magnetic signal. And the fact that these signals are on the rim is very problematic, right? Because these zircons, they've actually been eroded and sent down the river in ancient times. So the surface of these zircons are not the primary original surfaces. So whatever stuff is stuck to that surface came in later, right? So in this case, we can corroborate this with elemental maps of iron distribution in the zircon. So the zircon itself doesn't contain iron, but you can see these iron oxide coatings on the surface of this grain. So again, this shows that this stuff was adhered to the zircon after its formation. So we can contrast that to a modern zircon. This is less than 1 million years old. And we did the same kind of QDM mapping. We find that instead of around the edge of the zircon, we have sources that are deep on the inside. And that's what it looks like. So we did tomography on that zircon grain, the same one in the last slide. And there's that big dark crystal there. That's a crystal called apatite. It contains, in this case, iron oxide sub-inclusion. So it's inclusion within an inclusion. And that apatite grain, if you look from the top down, coincides exactly with the main magnetic signal of the zircon. There's a signal here. There was an apatite grain. It fell off by the time we took this image. You had to take my word for that.
So is there a reason, like, I think the other chart had like xenotime and monazite, right? There's all these sort of secondary phosphates. So is there a reason that those particular minerals are observed with these zircons because they're not chemically very similar, right?
Yeah, I think, as I understand, I'm not a geochemist, but as I understand, the phosphates they're much easier to mobilize with groundwater or with these metamorphic fluids compared to other silicate phases. So if you get, they're most sensitive indicators, right, of these recrystallization events. Okay, so what do we do about this? We have a bunch of ferromagnetic phases in the Jack Hill zircons that we think are secondary. So we can try to acid wash them. This is not the same zircon, by the way, but you can see in general these untreated zircons have a lot more iron. So this is again an iron map, and we can also see that the main ferromagnetic sources in these untreated zircons come from these incrustations, right? These rinds of iron oxide. Whereas at least in this one zircon, we have a nice internal source. So right now we're trying to do tomography and microscopy on these washed zircons to try to figure out if there's actually some sort of primary mineral under there. It might not be, but at least we know where to look now based on the QDM imaging. Okay, so what we've been doing is we acid wash these zircons. Turns out the vast majority of them lose all their magnetic signal when you acid wash them. It's not too surprising, I guess. We're almost done here. So this is a diagram of the magnetization as you demagnetize the zircon progressively. So I was talking earlier about how the fact you had to do many steps to do these experiments. Okay, so out of the 5 zircons analyzed so far, 3 of them basically lose all their magnetic moment immediately. So they have no information. So the other 2 kind of wobble around very noisily, and they have no more magnetization at about 500 degrees. Now, critically, we have to look for magnetization within this narrow window between about 550 and 580. 580 is a Curie point. There's nothing above that. Why above 520? And that's because we know the metamorphic temperature of the Jack Hills region. We know it's been heated to 520 in ancient times. All right, so any magnetization that's blocked below 520 is not going to tell you anything older than that last metamorphic event has been erased. So we see no signal here, which is unfortunate. So I think that either indicates that there's no ferromagnetic minerals that survive, in which case the result is that these zircons don't contain the necessary information, or the perhaps more intriguing scenario is that there's no geodynamo. Right? We had magnetic phases there, but they're not recording anything because they crystallize in a zero magnetic field on the early Earth. So to distinguish these, we have to go in and look for these minerals. If they're there, but are not getting magnetized, that would seem to indicate the no geodynamo hypothesis is right. But if they're not there at all, then, well, what can you do? By the way, this is the data from Tarduna et al. 2015. They got very different looking demagnetization spectra than we did. I'm not quite sure why this is, but they didn't do any acid washing. So one suspicion is that most of this is being carried by secondary phases. Okay, second to last slide. So just to conclude this terrestrial or early Earth section, we don't know if there's a field before 3.5 billion years ago, but we're trying very hard. Here's the conclusion slide, just to review. I don't have to read it out, I think, but the last thing I want to say is that we're actively developing this. So we should keep talking if you guys have any interest in working on this together. And we made a lot of progress in sensitivity and sort of just the robustness and not breaking downness of the setup. But we can certainly do a lot better, I think. Thank you very much.
Let's see, questions? What would you do if you had a large amount of money to improve your apparatus so that you could look at more crystals?
Yeah, there's a few things we want to add to this. Yeah, so right now we can only, so when we do the demagnetization, we actually take the sample off, demagnetize it either in the oven, which is actually this thing back here, or in an alternating coil, so alternating magnetic field. We can try to build that in to the setup, so you can put the sample on, wait a very long time, and it will actually just do the whole sequence for you, which will be very nice, very efficient, and also take out a lot of fiddling and errors. But I think that's going to be quite hard. We're going to have to change everything in the setup so they don't have eddy currents, and we have to work in a much stronger field regime when the coil is turned on. So talking to Ron about these developments, I think, yeah, they're a few years down the road, but I think if we had a large amount of resources right now, we can maybe get this to happen faster. And the other thing about the deep well cameras and just maximizing sensitivity is another issue. I'm not sure whether that's available or not. But.
Other questions? Yeah.
So when you measure some of these magnetic features with your QDM, you see these like little localized dipole type features.
Mm-hmm.
And then you were also doing some probing to try and see like an overall dipole of one of the grades. But you weren't seeing evidence of that. Would you not also see like an overall dipole envelope if there were some internal source as well as these like later added magnetic features on the surface?
Yeah, so we thought about this. So like this guy, for example, right? You're saying like if this whole thing has some weak magnetization, you should be able to see like a big dipole source kind of all around the whole thing.
A dipole envelope and then these localized point defects.
Yeah.
Is there some mechanism for mass, like for shielding the internal field or something?
There shouldn't be any shielding. There's all the permeabilities of these things is just like free space. These silicate phases. Yeah, so we did worry about this. So what if you had this like broad dipole feature we're just not seeing? So we can calculate just from the noise level, like what's the maximum dipole you can emit, and it's still much smaller than that source, and also much smaller than the measurements of the zircon from the 2015 paper.
Okay.
So I think.
So it could still be there beneath the noise floor.
No, it can't. That's what I'm saying. Yeah, the strongest dipole that we still couldn't see is still much weaker than the dipoles that they were seeing. So I think they were seeing something else, like that, for example.
Okay.
Yeah.
So if you made a squid measurement of this, it would look like a larger dipole.
Yeah, I think we'll basically be looking at that. Yeah, like that seems to be the dominant source in this zircon.
Hold on. Other questions? Last question. If not, let's thank them again.
What's the meteorite?
That's it.
Who has the meteorite?
Meteorite.
I have.
Okay.